Hello everybody, good morning. Myself, Dr. Shubhankar Sen, an Associate Professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the second lecture of the third module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall first illustrate a flow chart highlighting the sequence of steps in finite element approximation. We then introduce the concept of local coordinate system and correlate the local coordinate system with the global coordinate system. Next, we shall derive the expressions of shape functions for the two-noded or linear bar element, and then we shall provide the expressions of shape functions for a three-noded or quadratic bar element. Next, we shall compare similarities and dissimilarities of the finite difference, finite volume, and finite element method. And then, by considering the Poisson equation of heat conduction, we shall show how finite element method differs from the finite volume method. So, in the last class of the first week, we have discussed the development of finite element method from the variational method. In that context, we highlighted the steps in a finite element formulation. Here, we summarize that process again in terms of a flow chart. So, this is containing all the steps of the pre-processing step, the processing step, and the post-processing step. So, the first step is that the governing equation is given. We identify the order of the governing equation. The order of the equation divided by 2. Those many integrations we perform to derive the weak form. Then we consider the profile assumption of the degree of freedom. It means that how the degree of freedom varies within the domain that is assumed and that is governed by the approximate functions or the shape functions in case of the finite element. Then we discretize the domain. We generate these connectivity arrays, ID array, and the LM array. So these steps are coming under the pre-processing step. So here we are showing the pre-processing step. Next, this derivation of the element level matrix equation system, and then calculation of this matrix entry and vector entry by Gauss quadrature, and implementation of boundary condition, and then assembly procedure. This leads to the processor step. So the steps here where we use the Gauss quadrature to calculate the element level matrices and vectors. Then we implement the boundary condition, and finally after assembly we generate the global matrix equation system that is known as the processor step or the solver step of FEM. So this is FEM solver part or processor. And finally, the last step is after solution, we do the post-processing. So the solution of the global matrix equation system, this also comes under the processor part. And once we get, for example, the temperature, calculation of heat flux from the temperature, or for a fluid flow problem, calculation of stream function, calculation of vorticity, calculation of stresses from the velocity and pressure field comes under the post-processing step. So we should remember that this Gauss quadrature, it is performed for calculating the Kij terms and Fij terms, but if the geometry is simple in one-dimensional problems, or if we have a Cartesian mesh, we can calculate Kij and Fij without using Gauss quadrature. But when we have a complex geometry, then we don't have any choice. We have to certainly use the Gauss quadrature for performing evaluation of Kij and Fie. So Gauss quadrature, this is a numerical integration procedure gives K, IJE and FIE terms for simple or complex geometry problems. For 1D or Cartesian structured mesh, K, IJE and FIE can be obtained without using Gauss quadrature. So, for the Cartesian structured mesh, we can find K, IJE and FIE with the help of direct integration, where we take help of the local coordinate system. So now we introduce the concept of local and global coordinates. Consider a domain. This is omega and this is x equals to 0 and this is x equals to 1. This is the continuum domain. In 1D, now we discretize the domain. This is the global coordinate system x and this is the origin of the coordinate system. Now we discretize the domain by a certain number of elements. So this is element 1, element 2, element 3, element 4 and element 5, and this is the mesh size or grid size delta x. This is the x direction. Now the nodes are common to multiple elements, okay, except the boundary nodes. For every node we have two different identities. If the identity is unique, then we say that we are using the global node number. If the identity is repetitive, then we say that we are using the local node number. So every node in the mesh has two identities, local or repetitive, global or unique. So this is FEM mesh. Now global numbers are unique, so every node has a unique number separate from the other nodes. So here we have nodes 1, 2, 3, 4, 5 and 6. So these are the global nodes. We denote them by capital A. A discrete element, it is shown here as element E with two nodes. These numbers, these are known as the local node numbers, local nodes, and the mesh size is delta x. These numbers are present in every element. So for element 1, we can denote them as 1, 2. First node is local node 1, second node is local or elemental node 2. For the second element, we have first node as local node 1, second one is 2. Like that, we can assign these local node numbers 1 and 2 for every element. Therefore, we can say that local node 2 of element 1 equals to local node 1 of element 2 equals to global node 2. So this is a local global correspondence, and that correspondence is known as the IEN array that we have already discussed. Now we introduce the concept of local coordinate system, which is very convenient in performing integration while calculating the K, IJE and FIE terms for one-dimensional problems or for problems in 2 dimensions or even in higher dimensions. If our mesh is of Cartesian type, it means that if our mesh is structured and if our grid lines are parallel to the Cartesian coordinate axis. So we denote the actual coordinate system as the global coordinate system. So x is the global coordinate system in this coordinate system, every location has a unique data. Now, we can define a local coordinate system associated with every element. So the local coordinate system, it stretches within that element of interest, and then the first local coordinate, it represents the zeroth data of coordinate, and the second coordinate represents the mesh size. It means that we introduce the concept of local coordinate system whose origin matches with the first local node of every element. So this local coordinate system is movable. We move the local coordinate system starting from element 1 up to the last element, while the global coordinate system, it is unique or it is fixed, and then we get the actual coordinate with respect to the global coordinate system. Now, this previous picture which we have shown, if we redraw it here, it is having 5 elements. So this is our global coordinate system. This is element 1, element 2, element 3, element 4, element 5, and then this is the origin. This is x equals to 0, this is x equals to 1. Now the coordinate of the second node of element 1 or the first node of element 2 with respect to the global coordinate system, it is denoted by the symbol x1e, and the second node of the second element, its global coordinate is x2e. So x1e and x2e are measured with respect to the origin of x or global coordinate system, or x1e and x2e are global coordinates. Now let us consider e equals to 2. So we fix a coordinate system whose origin overlaps with the first local node of element 2. We say that this is the local coordinate system x bar. So this is the origin, this is x bar equals to 0. So x bar equals to 0, it matches with the x1e coordinate of the global coordinate system. So we can see that the distance between x and x bar, the difference is x1e. So if we look into this picture, so the linear distance between the global coordinate system and the local coordinate system, considering element 2, this is by the distance x1e. So we get a transformation formula x equals to x bar plus x1e. Okay. Similarly, we can write y equals to y bar plus y1e if we want in the y direction or in the vertical direction. Using this relation, using x equals to x bar plus x1e, we get when x equals to x1e, this gives us x bar equals to 0, and when x equals to x2e, we get x bar equals to x2e minus x1e equals to delta x. So x bar varies from 0 to delta x. Now similarly we can vary y bar also from 0 to delta x. So if we consider a two-noded bar element, local node 1, local node 2, this is the element E, and then its origin starts from here, x bar This is the local coordinate system, and then here we have the global coordinate system x bar. This is x, so this is global coordinate system origin, and this is the local coordinate system origin. So this distance, this is x1e, and this distance, this is x2e, and this mesh size is delta x. So for local node 1, x bar equals to 0. For local node 2, x bar equals to delta x. Now, if we consider a 3-noded bar element or a quadratic element, so x bar goes in this direction. So this is x bar equals to 0. This is x bar equals to delta x. For node 2, this is x bar equals to delta x by 2. Here, delta x is the size of the element. Now, this concept can be extended to 2 dimensions or even in 3 dimensions. If we go for 2 dimensions, let us consider for the Cartesian element, we should remember that if the edges of the element are parallel to the Cartesian axis, then only this transformation is valid. So, if we have a quadrilateral element, a bilinear type, so this is the global coordinate system, xy, this is the origin, 0, 0, the local nodes 1, 2, 3, and 4. In the counterclockwise sense, we always do the numbering. Then, the mesh size is delta x. Here, the mesh size in the y direction, this is delta y. So, we know that the origin we have to put with the first local node for the local coordinate system, x bar and y bar. So this origin's coordinate is 0, 0. This is 0 delta x. This is delta x, delta y. And this is 0 delta y. So these are the x bar, y bar data. Okay. And the actual distance from the origin of the first local node is, this is x1e and this is y1e. So we use x equals to x bar plus x1e, y equals to y bar plus y1e. So this is in 2 dimension. This is bar element of quadratic type. This is bar element of linear type. Now, this transformation is valid only for the elements whose edges are parallel to the axis of the Cartesian coordinate system. So this we should remember. This is not universally applicable. This is only applicable for elements. Those are Cartesian as well as structured. Now, we provide little more information about the shape function of bar elements. To this end, we shall consider the linear and quadratic bar elements. So first we consider bar elements of linear type. 2-noded bar elements. So this is an arbitrary element E which has 2 local nodes 1 and 2. Now, we consider that a degree of freedom, such a temperature, it varies linearly within the element. So let a DOF such as temperature equals to Tx varies linearly along E, along the element E. Okay. So, with respect to the global origin, the coordinates of the nodes are, this is the origin. So from here, the global coordinates of nodes 1 and 2 are x1e and x2e. Now, we have to find out the expression for psi1ex and the psi2ex. These shape functions, we already know that if the temperature is varying linearly within this element, it means that both of the shape functions, they must also be straight lines. So we assume that Tx equals to a plus bx. This is the linear polynomial. Now we have two boundary conditions. At node 1, our temperature is given as T1e. At node 2, our temperature is given as T2e. So this T1e and T2e, they act as boundary conditions for finding the values of A and B. So find A and B by using the boundary conditions, essential boundary conditions on temperature, that T at x1e equals to T1e and T at x2e equals to T2e. So implementing these boundary conditions, we get T at x1e equals to T1e equals to A plus B x1e and T at x2e equals to T2e equals to A plus B x2e. From here, we have to find out A and B. So subtracting, we get T2e minus T1e equals to B into x2e minus x1e, or B equals to T2e minus T1e by x2e minus x1e. Now we can substitute this value into any of these equations and we can find out the value of A. So using T1e equals to A plus B x1e, we get T1e equals to A plus B means T2e minus T1e by delta x into x1e. This gives us A equals to T1e minus T2e minus T1e by delta x into x1e equals to T1e delta x minus T2e x1e plus T1e x1e by delta x equals to T1e x2e minus T1e x1e minus T2e x1e plus T1e x1e by delta x. So from here we get A equals to T1e x2e minus T2e x1e, T2e x1e. So putting A and B in Tx equals to A plus Bx, we get Tx equals to a plus bx equals to T1e x2e minus T2e x1e by delta x plus our b was T2e minus T1e by delta x into x. So this is actually T2e minus T1e by delta x. So from here we get T1e into x2e minus x by delta x plus T2e into x minus x1e by delta x. So we got here Tx equals to T1e into x2e minus x by delta x plus T2e into x minus x1e by delta x. Now the trial solution for unknown DOF is Tx equals to summation of Tje psi je x for j equals to 1 to nen. Here our nen is 2 equals to psi 1e psi 2e into T1e T2e. So this can be written as T1e psi 1e plus T2e psi 2e. So from here psi 1 ex equals to x2e minus x by delta x and psi 2e x equals to x minus x1e by delta x. Now these are the Lagrangian shape functions and they satisfy the properties of the Lagrangian shape functions that we have mentioned before, that summation of them should be 1. At a given node, the given shape function is unit valued. At the other node, the value of the shape function is 0. So these are the Lagrangian shape functions. These are straight lines of contrasting slope. So this is the element, the local nodes number 1, local node number 2. Then this is our psi 1 ex, and this is our psi 2 ex. These are two straight lines. So these are local shape functions. These are shape functions in terms of global or actual coordinates. Okay. So when we do FEM calculations, the shape functions, they are converted in terms of the local coordinate system for performing the numerical integration or the Gauss quadrature. Now, these shape functions, they satisfy psi 1 ex plus psi 2 ex equals to 1. They satisfy, and psi 1e at x2e, it will be 0. Psi 1e at x1e, it will be 1. Psi 2e at x1e will be 0. And psi 2e at x1e, it will be equals to, and psi 2e at x2e, it will be equal to 1. So these are the basic properties of Lagrangian shape functions. Now we can write these two expressions in a very compact form, that psi I e equals to minus 1 to the power j xj e minus x by delta x, where I and j vary from 1 to 2 such that I is not equals to j. So psi I equals to 1, then j will be 2. So psi 1 e equals to minus 1 to the power 2 into x2e minus x by delta x. So psi 1e equals to x2e minus x by delta x. I equals to 2, then j equals to 1. So this gives us psi 2e x equals to minus 1 to the power 1 x1e minus x by delta x minus x1e by delta x. Now by substituting x equals to x bar plus x1e, we get psi 1e x bar equals to x2e minus x1e minus x bar by delta x 1 minus x bar by delta x, and psi 2e x bar, similarly it can be shown that it comes as x bar by delta x. So these are shape functions using local coordinates. Now these same shape functions can be used for calculating the kij terms and fie terms for a given problem. We can extend this concept for the quadratic bar elements. So we can fit a parabola as a plus bx plus cx square. Then we can calculate the coefficients a, b, and c by using Cramer's rule, and then we can find out psi 1e, psi 2e, and psi 3e. So for a quadratic bar element, we have three nodes, nodes 1, 2, and 3. So we shall have psi 1e, psi 2ex, psi 3ex. Since this is a quadratic polynomial, it means that it is a parabola. So every shape function will look like a parabola. These shape functions, if we plot them, so this is psi 2ex, this is psi 1ex, and this is psi 3ex. So this is psi 3ex. So this is 1, 2, 3. So this value is 1. This psi 1e, psi 2e, psi 3 are parabolic. So we can use Tx equals to a plus bx plus cx square. Now we can think of the global coordinates as x1e, x2e, and x3 with x t of at x1e equals to t1e, t at x2e equals to t2e, and t at x3e equals to t3e. So by using these boundary conditions in this parabola, we can get a 3 by 3 matrix equation system. We have to solve it. We can use Cramer's rule, and then we can find out the coefficients a, b, and c. And in the same way, we can find out the psi 1e, psi 2e, and psi 3e quantities. So this coordinate is with respect to an origin. This is x1e, this is x2e, and the last local node, its global coordinate is x3e. Now, the transformation formula is valid for the bar elements of any type. X equals to x bar plus x1e transformation is valid for bar elements of any order. It means that even though we have shown it for two-noded bar elements, it can be extended also for three-noded bar elements. If we consider the Lagrangian shape functions for the quadratic elements without derivation, we shall show here psi1e as a function of x, psi2e as a function of x, and psi3e as a function of x. So these are all nonlinear curves, or these are parabolas. So here we shall have x3e minus x1e into x2e minus x1e. So we have here x3e minus x and x2e minus x. Similarly, for the second we have x3e minus x2e into x1e minus x2e. Here we have x3e minus x into x1e minus x. Finally, here we have x2e minus x3e into x1e minus x3e. Here we have x2e minus x into x1e minus x. These are all parabolic curves. So this is coming from a general formula of obtaining Lagrangian shape function of bar elements of any order, of any finite order. So in these expressions, if we put the transformation relation x equals to x bar plus x1e, it can be found that psi1e x bar equals to 1 minus x bar by delta x into 1 minus 2x bar by delta x. Psi2e x bar equals to 4x bar by delta x into 1 minus x bar by delta x. And psi3e x bar equals to minus x bar by delta x into 1 minus 2x bar by delta x. These expressions are useful in calculating the Kije and Fie terms for quadratic elements. So here I redraw the quadratic element, local nodes 1, 2 and 3. The mesh size is delta x. With respect to the global coordinate system, the coordinates are x1e, this is x2e, and this is x3e. So this is the origin. So we can say that this is the origin of the x coordinate system. Then this node 2 is located at the middle of nodes 1 and 3. This is a very important criterion. Node 2 cannot be located randomly. If we put it randomly, we get a singular matrix in the calculation of psi1e, psi2e and psi3e. And here, if we go for the local coordinate system, so x bar equals to 0 for local node 1, x bar equals to delta x by 2 for local node 2, and x bar equals to delta x for local node 3. So here we provide a comparative account of the three basic fundamental discretization techniques: finite difference method, finite volume method, and the finite element method. So first we go for the finite difference method. Here it is finite volume method, and finally it is finite element method. So FDM is not a variational method. There is no explicit integration. In fact, FDM is equivalent to numerical differentiation. This is the first point. FVM is a variational method. FEM is an improved variational method. In FDM, discretization starts directly from nodes. In FVM, discretization starts from the cell and ends at nodes. In FEM also, discretization starts at elements and ends at nodes. FDM does not work on unstructured mesh. FVM works on unstructured mesh. FEM certainly works on unstructured mesh. Coordinate transformation is must for complex geometry problems. Coordinate transformation in finite volume may or may not be needed. In finite element, coordinate transformation is not needed. The transformation from xy or physical plane to xi eta or natural plane is a change of variables. So when we go for coordinate transformation in finite difference, we have forward transformation and then we have a reverse or backward transformation. Fifth difference is that the natural boundary condition is treated separately. In FVM also, the natural boundary is treated separately. In FEM, NBC becomes part of weak form and no need for separate treatment. Point 6. In FDM, there is no concept of weight function. In finite volume, value of weight function in finite volume is 1. Weight function varies between 0 and 1 in FEM. So these are the some of the differences or comparison among these three fundamental methods. We can highlight some more differences. So some more differences are FDM, FVM, FEM. So this is seventh difference. For non-essential type of boundary conditions, Laplacian operator may not yield symmetric matrix. Same for the finite volume method. The matrix from Laplacian operator del square may not be symmetric for non-EBC nodes. The Laplacian operator in FEM always gives symmetric element level or global level coefficient matrix. For transient problems, the explicit formulation in FDM, the explicit formulation gives diagonal coefficient matrix. Same for the finite volume method. A diagonal coefficient matrix develops from explicit formulation of transient problems. A non-diagonal, in contrary with FEM, a non-diagonal mass matrix, we shall discuss it when it will come. A non-diagonal mass matrix forms via explicit FEM discretization of transient problems. This mass matrix may be diagonalized via mass lumping. In FDM mesh generation does not require connectivity array. only coordinate array is sufficient. So structured mesh generation in FVM does not require connectivity array, but connectivity array is compulsory. Array is a must for mesh generation using the finite volume method. So these are some basic differences or some similarities among these three methods. There are certainly many more points. So now we discuss the fundamental differences in the finite volume and finite element technique with respect to the Poisson equation in 2 dimensions. So we shall highlight comparison of FDM, FVM and FEM in terms of discretization of Poisson equation in 2D. So let us only consider the strong form of the governing equation, k del square t plus q equals to 0. This is the Poisson equation of heat conduction, where T is the degree of freedom. In 2D, this equation becomes K del 2T del x2 plus del 2T del y2 plus Q equals to 0. Let us first discuss the finite difference discretization. So we have the orthogonal grid here, which is compulsorily structured. Now we have grid lines I plus 1, I plus 2, I minus 1, I minus 2. This is J, this is J plus 1, this is J minus 1, this is J minus 2. So this is the ijth node. Now, when we discretize the governing equation, plus del 2t del y2 at the ijth node plus q at ijth node equals to 0, we certainly use only the second order central difference scheme for the diffusion term. So this is a diffusion term which is having no directional bias, and because of that we have to use central difference in finite difference and finite volume and Galerkin in the finite element method. So by discretizing using CDS, using the central difference scheme of order 2, we get k into ti plus 1 minus 2ti plus ti minus 1 by delta x whole square plus tij plus 1 minus 2tij plus ti comma j minus 1 by delta y whole square plus q equals to 0. From here we can simplify it as ti plus 1 minus 2ti plus ti minus 1 plus delta x by delta y whole square into ti comma j plus 1 minus 2tij plus ti comma j minus 1 plus q into delta x whole square equals to 0. Now the finite difference grid may be uniform, may be non-uniform. The aspect ratio of the grid we define by the symbol beta. So define beta equals to delta x by delta y equals to grid aspect ratio. So Now the equation can be simplified as ti plus 1 minus 2ti I plus 1j minus 2tij plus ti minus 1j plus beta square ti comma j plus 1 minus 2 beta square into tij plus beta square ti comma j minus 1 plus q by k delta x whole square equals to 0. This can be written as 2 into 1 plus beta square into tij minus ti plus 1 comma j minus ti minus 1 comma j minus beta square ti comma j plus 1 minus beta square ti comma j minus 1 equals to q by k into delta x whole square. So this k is missing here, and this is mesh size or grid size delta x, and this is delta y. Now the expression which we get here, that is the generalized finite difference discretized algebraic equation. This is a linear algebraic equation because our original governing equation was linear. So this is FDM discretized linear algebraic generic equation. If we note, there are 5 terms in the left hand side, 5 temperatures. The coefficient of each temperature, they will give us one diagonal. So it means that in this case we shall get a pentadiagonal matrix equation system as opposed to the tridiagonal matrix equation system in one dimension. One difference is here that the pentadiagonal matrix system will have one remote superdiagonal and one remote subdiagonal. It means that there will be 3 diagonals adjacent, the main diagonal, the main superdiagonal and main subdiagonal. They are adjacent. After that, there will be some 0 diagonals followed by one non-zero superdiagonal and one non-zero subdiagonal. So this is the finite difference discretized generalized equation. Now it will be shown here that as long as the mesh is Cartesian and structured for the given problem, finite volume method gives us exactly the same linear algebraic equation. So the finite difference and finite volume methods, they overlap for the Cartesian structured mesh, but it does not hold for the finite element method. The final matrix equation system for this problem that generates from the finite element method, that is different from both of finite difference and finite volume method. So here we highlight the key difference between the FEM and FVM with respect to the given problem. So FVM and FEM discretization of Poisson equation in 2 dimensions. In both cases, we start with MWR. Here we mention that FVM is a special case of FEM. For FVM, the weight function is always constant, it is unit valued. So I have written Wx to indicate it is in one dimension. We can represent in multi dimensions. So weight function is a constant for the finite volume method. So this makes a massive difference between the finite volume and finite element method in terms of the generation of the equation system. So using the MWR statement, we have integration over omega e. Let us start directly from the omega e w r d omega e equals to 0. We know this. So for our case, r was k del square t plus q d omega e equals to 0. We know that this gives us minus integration over omega e gradient of w dot gradient of thermal conductivity is there, gradient of temperature d omega e, plus we have the flux term integration over gamma e w into k del t del n. This is the secondary variable term d gamma e plus integration over omega e wq d omega e equals to 0. Now, if we see here, this is the weak form of the Poisson equation. For FVM w equals to 1, it renders gradient of w equals to 0. Therefore, for FVM, the weak form simplifies to boundary integral over gamma e w k del t del n d gamma e plus integration over omega e wq d omega e, or integration over gamma e wk del t del n d gamma e equals to minus integration over omega e wq d omega e. Now, this is the flux term. So, in finite volume method, we know that it operates on the balancing of fluxes across a cell. So, this flux term, this will give us the matrix equation system, and the right hand side source term, this will give us the load vector. So, this is a fundamental difference. Because of this imposition of W equals to 1, the finite volume method, it loses a considerable amount of accuracy by dropping the term of gradient of W dot gradient of T, which is present in the finite element method. Because of this term, the finite element method, it generates the matrix from gradient of W dot gradient of T term or the diffusion term. What finite volume method generates the coefficient matrix from the flux term. So in finite element method, this term is present. In FEM, the stiffness matrix Ke is obtained. Ke or K assembled matrix K is obtained from gradient of W dot gradient of T d omega e term. In FVM, the K matrix is obtained from boundary integral of gamma e W K del T del n d gamma e term. Therefore, there is loss of accuracy in FVM as compared to FEM for a given problem, particularly in multi dimensions. The difference between these two methods is not much appreciable in one dimension, but when you go for multi-dimensions, then the difference becomes prominent. So we have shown one numerical problem in this week where we shall consider the comparison of finite difference, finite volume, and finite element solutions for Poisson heat conduction equation in one dimension. Interestingly, it is found that all three methods, they converge to the same solution set, and that solution set also agrees well with the exact solution or the analytical solution. Now, coming back to the finite volume method, our integral form is for FVM, our simplified integral form is boundary integral over gamma e w into k del t del n d gamma e equals to minus integration over omega e w q d omega e. Since w equals to 1, we can get as integration over gamma e k nx into del t del x plus ny into del t del y d gamma e equals to minus q into integration over omega e d omega e. This is in two dimensions. Del t del n equals to nx del t del x plus ny del t del y. Now we can consider some cells for our finite volume analysis. So this is delta x, this is delta y, this is our cell of interest. So we consider a central point P. This is the east neighbor, this is the west neighbor, this is the north neighbor, and this is the south neighbor. This is the global coordinate system. This is the origin of the global coordinate system. Then we have the east face, the west face, the north face, and the south face. So if we zoom this picture here, for this is the cell P, this is the south neighbor, this is the east neighbor, this is the north neighbor, and this is the west neighbor. So this is the east face, this is the north face, this is the west face, and this is the south face. Now across all faces we have the unit normals. So this is unit normal, unit normal, unit normal, unit normal. So here nx equals to 1, here ny equals to 1, here ny equals to minus 1, here nx equals to minus 1. Now this term we can split into edges of the given cell. So this can be written as integration over gamma west e k into, here nx is minus 1, so it is minus 1 into del t del x d gamma e d gamma west e plus integration over gamma south e k. Here for this left face, for this west face, ny was absent, that term does not come. For the south face, nx does not exist, so ny is minus 1, k into minus 1 into del t del y d gamma e. For the east face, we have integration over gamma e k into 1 into del t del x into d gamma east plus integration along gamma north e k. Here ny is positive, so ny is 1, then it is del t del y d gamma e equals to minus q into omega e. Now omega E equals to delta x into delta y. So here we get, from this equation, we get minus k del t del x at the west face into delta y minus k del t del y at the south face into delta x plus k del t del x at the east face into delta y plus k del t del y at the north face into delta y at the north face into delta x equals to minus q into delta x into delta y. So this gives us minus k into del t del x at the west face equals to Tp minus Tw. It is Tp minus Tw by delta x into delta y. So these distances are equal to the grid size. So this is delta y minus k into del t del y at south face is Tp minus Ts, Tp minus Ts by delta y into delta x plus k into del t del x at the east face Te minus Tp by delta x into delta y plus k into del t del y at the north face, it is Tn minus Tp, Tn minus Tp by delta y into delta x equals to minus q delta x delta y. So this term we can simplify here as Tp minus Tw. So this is simplified as minus Tp minus Tw divided by beta, delta x by delta y equals to beta, minus Tp minus Ts into beta plus Te minus Tp by beta, Te minus Tp by beta plus Tn minus Tp into beta plus Tn minus Tp into beta equals to minus q by k delta x delta y. So we can write it as minus Tp plus Tw minus Tp plus Ts into beta square plus Te minus Tp plus Tn minus Tp into beta square equals to minus q by k delta x delta y, which can be further simplified as minus 2 into 1 plus beta square into Tp plus Tw plus T east. So this is T plus beta square Ts plus beta square Tn, beta square Tn equals to minus q by k into delta x delta y. The final version of the finite volume discretized linear algebraic equation is given as 2 into 1 plus beta square into Tp minus Te minus Tw minus beta square T south minus beta square T north equals to Q by K into delta x whole square. Now we can correlate the nodal points P, E, W, S, N with respect to the indices I and J that we use in the finite difference method. So here we redraw the mesh. Now we can consider this cell containing the node P. Then we have the nodes E, W, north and south. This node P, it can be thought of the node Ij. So P corresponds to the position I comma j, then E corresponds to I plus 1 comma j, and W similarly corresponds to I minus 1 comma j. Similarly, the northern node, it can be represented as I comma j plus 1. And finally, the southern node, it can be correlated as I comma j minus 1. Now, substituting this P, E, W, S and N by using the indices I and J, we can rewrite the above equation as, in terms of Ij indices, the above linear FVM discretized algebraic equation is expressed as 2 into 1 plus beta square T of I comma j minus T of I plus 1 comma j minus T of I minus 1 comma j minus beta square T I comma j plus 1. This is for north, and then for the south we have beta square T I comma j minus 1 equals to Q by K into delta x whole square. So this expression is exactly the same as we have obtained using the finite difference approximation. So for a Cartesian mesh, we have the same generic form of the discretized algebraic equation when we use finite difference as well as finite volume methods. So this is the generic algebraic equation. So generic FDM or FVM discretized linear algebraic equation when the mesh or grid is structured and Cartesian. We show the difference between finite volume and finite element method in regard to the Poisson equation in 2 dimensions. So FEM in 2D for Poisson equation. Let us consider an one-dimensional case first. In 1D, let us consider this is a node, this is ith node, this is I plus 1th node, and this is the I minus 1th node. When we write the finite difference equation, we have Ti minus 1 minus 2Ti plus Ti plus 1 using finite difference method. If we use finite volume method, then also we get the same expression. Using finite volume method also we get the same expression, Ti minus 1 minus 2Ti plus Ti plus 1. So it means that when we use finite difference and finite volume method in one dimension, we get exactly the same generic equation. So in these equations, I have shown only the left-hand side portion. Now, when we use the finite element method for the same problem in one dimension, it is found that the equation obtained from finite difference and finite volume method, they do not differ from those obtained using the finite element method. Let us consider the same picture for the mesh. So we have 3 nodes. Now, if we consider that the global equation numbers for this case are 1, 2, and 3, and the unknowns are T1, T2, and T3, then equation at global node 2, they will be coming from global node number 1 as well as global node number 3. So if this is element E and if this is element E plus 1, then we know that our LM array, it can be written as E1, 2, A, 1, 2, I, 1, 1, N, E, 1, 2. So here we get for the first element, the equation numbers are 1 and 2, and for the second element, the equation numbers are 2 and 3. So when we write the equation at global node 2, we get K21 T1 plus K22 T2 plus K23 T3 equals to F2. So here, this is the node at which we are writing this equation. Now, we can see that for the particular case we have considered, this equation at node 2, it is taking the help from nodes 1 and 3, and then when we put the values of K21, K22, and K23, we find that this algebraic equation, it matches exactly with the finite difference or finite volume counterpart. Now, when we go for the two-dimensional case, this does not hold. So let us consider a two-dimensional case for the Poisson equation that we have already considered for the finite difference and finite volume methods. We want to write the governing equation at this node I, j. So we have I plus 1, j, we have I minus 1, j, we have I, j plus 1, and we have I, j minus 1. So this is I plus 1, j plus 1. This is I plus 1, j minus 1. This is I minus 1, j plus 1. And this is I minus 1, j minus 1. So let us consider these elements as element E plus 1, element E plus 2, and element E plus 3. Now, the node I, j is common to all 4 elements of interest or elements E, E plus 1, E plus 2, and E plus 3. Therefore, all the nodes belonging to these four elements will contribute to the global equation at node I comma j. If we look at this mesh, then we see that there are 9 nodes. There are 9 nodes that belong to E, E plus 1, E plus 2, and E plus 3. It means that all these 9 nodes, they will be present in the global or assembled matrix equation system at the ijth node. It means that when we deal with the finite element method for the same mesh structure, we have 4 extra coefficients. So this northeast coefficient I plus 1, j plus 1, the northwest coefficient I minus 1, j plus 1, the southwest coefficient I minus 1, j, and the southeast coefficient I plus 1, j minus 1. These 4 are the extra terms that contribute to the finite element equation. It means that the finite element equation for the same problem will be denser. So it means that when we write the ijth equation, we can write it as k ij Tij plus k I plus 1j T I plus 1j plus k I minus 1j T I minus 1j plus k I j plus 1 T I j plus 1 plus k I j minus 1 T I j minus 1. So up to these terms, they are common in the finite difference method as well as finite volume method. Now in finite element method, the extra terms are k I plus 1 j plus 1 T I plus 1 j plus 1 plus k I minus 1 j plus 1 T I minus 1 j plus 1 plus k I minus 1 j T I minus 1 j plus k I plus 1 j minus 1 T I plus 1 j minus 1 equals to f I comma j. So these 4 terms, these are the extra terms in FEM. So these terms, they are present in FDM and FVM. It means that in FEM, for the same problem, we get a matrix of 9 diagonals. Okay, so we are getting 4 extra diagonals. They are coming from the 4 corners that are not considered in the finite difference or finite volume method. In particular, when we find the del 2 t del x del y type of terms, these cross derivative terms like del 2 t del x del y that appear in the stream function vorticity formulation for pressure instead of temperature, then we get this kind of mixed derivatives. So when we discretize the mixed derivative by using finite difference approximation, then we get these 4 corner nodal points I plus 1 j plus 1 I plus 1 j minus 1 I minus 1 j plus 1 I minus 1 j. Now using bilinear quadrilateral elements in finite elements, these 4 corners, they contribute to the discretized algebraic equation. So for example, this is a finite element, just we are showing it. So this is a bilinear quadrilateral element. So now we have clearly shown the differences between finite difference, finite volume, and finite element method in terms of the element level or the global level equation generation. The equation which I have shown here, this is the global equation system. Here, this kij, ki minus 1j, this kind of terms, they are just representative. they will be constructed by taking contributions from individual elements. So I conclude today's class here. So in this class, we have highlighted the similarities as well as differences among finite difference method, finite volume, and finite element methods. Then we have also compared the final matrix equation structure for FDM, FVM, and FEM in 2D. For the FEM, we did not show the full matrix. We have shown only one equation. So that gives us an idea that we shall get a banded matrix with 9 diagonals. For today's class, I recommend the books by Professor Patankar, then the Professor Anderson's book on finite difference method on CFD. Then for FEM parts, I recommend the books by Professor Hughes and Professor Reddy. Thank you very much for attending today's lecture.